That's right. Yes. Food's so good you'll never leave.
Food's so good you physically won't be able to leave.
Yes. And it won't be the food poisoning. Food's so good, you'll eat so much that you will become a black hole, and therefore you will be in there inevitable. Okay, anyway.
It'll be your own spaghetti.
It'll be, yeah, something.
The spaghettification factory. Spaghetti factory.
Spaghettification warehouse.
Oh. Designer spaghetti warehouse.
Well, all right, moving on. Sources of opacity in a stellar atmosphere.
That's not spaghetti.
That's not spaghetti. I'm glad that you recognize that. We're making some progress here.
No more raising a fool. When you show up for dinner and you're like, wait, this is not true, this is physics.
Yeah.
Doesn't have to be tricked again.
Yes.
First you some one large like trick into doing physics.
That's right.
It's not a mind illusion. Wait a second, no.
So number one is what we call bound-bound absorption. And the bound refers to the electron is bound to an atom when it starts and bound to an atom when this is done. Later we'll talk about free, bound, free. So in other words, bound and free will refer to is the atom orbiting a nucleus or is the atom, is the electron orbiting a nucleus or is it free? I'm free. So bound absorption. So that is occurring when an electron bound to an atom absorbs a photon, jumps up to a higher energy level. The classic thing that makes absorption lines, in other words. Occurs when an electron bound to an atom absorbs a photon and jumps to a higher energy level. So it's going to jump to a higher energy level. It's not going to stay there. It's going to want to jump back down again. So one thing that can happen is it jumps up and then it jumps back down to the same level. And in that case, effectively what has happened, because it doesn't typically take very long to do that, is the net effect is the photon is scattered because it's like, shoop. And then when it's spit out, it'll be spit out in some, when a new photon really is spit out, it'll be spit out in some random direction. But if the upward transition and the downward transition are between the same two levels, essentially it's the same wavelength photon. And not quite, because momentum conservation says that you have to give some kinetic energy to the atom. And so when it spits out the new photon, there will be a little bit of a Doppler shift. But to an awfully good approximation, atom eats photon and then shortly thereafter spits out an equivalent photon moving in a different direction. So in other words, effectively that's a scatter. It's as though you simply redirected the photon. So if the electron falls back down to the same level, as it started in, the net effect of this is a scattering. In which V, I'll put it in quotes, photon's energy stays the same, but its direction changes. quotes because it's not really the same photon, strictly speaking. Because once a photon is absorbed, it disappears and a new one is spit out when the transition happens again. But that's a minor point.
So you're going to teach us now?
Yes.
What's that?
So you're going to teach us now?
That's right, yes. Okay, take it over. It's like, I've had enough of this. Let me do this right.
Now that we're messing, should be over.
Yes, that's right, let me take over now. I'm tired of Harmon confusing you guys all the time. Because that maximizes embarrassment. On the other hand, you can also have like, what if it's in the ground state of a hydrogen atom, it absorbs an ultraviolet photon, kicks up to n equals 4. Well, the electron might not jump all the way back down to the ground state, it might jump from 4 to 3, and then from 3 to 1. So then you get 2 photons out where 1 photon went in, and essentially the original photon's energy has been subdivided into the energies of multiple longer wavelength photons. So you can thereby change the distribution of number of photons with wavelength via this process. So if the electron makes multiple downward transitions through intermediate energy levels, the effect is a degradation of the mean photon energy, because there's more photons that have lower energies on the other side. If the electron makes multiple downward transitions through intermediate energy levels, the effect is a degradation of the mean photon energy. So that is bound-bound absorption. Do you have a question? Yeah.
Yeah, so the multiple downward transitions just be one jump.
No, multiple jumps. In other words, what if you look at like the hydrogen energy level diagram, what if it jumps from n equals 1 to n equals 4, and then instead of jumping all the way down, next thing is the electron does that, and then it does that. And 1 photon went in, but 2 photons came out. The sum of these photons' energies is equal to this photon's energies. So the average photon energy is lower now because now we have 2 lower energy photons instead of 1 higher energy photon. And basically, all the possibilities happen. In other words, sometimes it jumps all the way back down to where it started, but every other combination is possible too, that you can imagine. So it gets complicated, and you have to do like the thermodynamics to figure out what really happens, and the quantum mechanics. The quantum mechanics tells you the probabilities of the various transitions. Let's do that. So the Schrödinger,
Not again.
not again.
Please no.
Well, because you don't want to, we will. So the Schrödinger, yes. Bound free absorption is another source of opacity. This is also called, good word, photoionization. That sounds much fancier than bound free absorption. Photoionization simply means ionization by a photon, ionization by light. Occurs when a photon has enough energy to ionize an atom. For example, a photon with 15 electron volts has enough energy to strip an electron out of the ground state of hydrogen because that takes 13.6 electron volts. So if photons have high enough energies, they can strip electrons off, and that process is called either bound-free absorption because the electron starts bound but ends up free, or photoionization to emphasize its ionization by light photons. Occurs when a photon has enough energy to ionize an atom. I have so much room here. I never have to hit return. Well, maybe not ever, I just have to hit return. Yeah. I hit return. This cursor can't move as fast as my computer does. For a hydrogen atom in state n, so by which I mean principal quantum number is some value n, 2 or 3 or whatever, it turns out that is definitely going to wave those chicken feet. This would be some detailed calculus. Well, let's do it. So the Schrödinger equation. It turns out that the bound-free absorption cross-section, sigma bound-free, is 1.31 times 10 to the minus 19 meters squared. Remember, cross-sections are effective areas that the atom is showing to the incoming beam of photons, times, so a constant out front that comes from evaluating a bunch of coefficients, times 1 over n to the 5th power times the wavelength over 500 nanometers. Very intuitive. And I will point out here, since we haven't said it explicitly at this point, a cross-section like that, what it represents is the ratio of the number of absorptions per atom per second divided by the number of incident photons per square meter per second. That's what a cross-section represents. And the idea would be suppose I had a 1 meter by 1 meter square, and you imagine a bunch of photons coming in, flowing through that square. There's a beam of photons. And imagine that your atom was just a sphere, such that if it hits the atom, it's absorbed, and if it misses the atom, it keeps on going. Of course, atoms are not hard spheres. It's more complicated, it's more complex than this. But the idea is, what if it was as simple as that? You just have this hard sphere that eats any photon that hits it, and lets pass any photon that misses it. It's all or nothing. If it hits the atom, it's absorbed. If it misses the atom, it isn't. It's more complicated than that because the photon can hit the atom, but it only has a certain probability of causing a transition. And the closer it passes to the center of the atom, the better the probability of it being absorbed. It's more complicated than that. But what if it came down to, if it was just a hard sphere? So the idea would be that if this sphere had cross-sectional area sigma, literal cross-sectional area, sigma, then sigma over 1 square meter should be the fraction of photons that get absorbed. Its area divided by 1 square meter should be the fraction of photons that get absorbed. See what I mean? Because the probability, if I'm just in some random part of the square, this area divided by 1 square meter is the chance that I will bump into the photon. Fraction of photons that hit that. is sigma over 1 square meter, would be the idea there. So, in other words, the number of absorptions divided by the number of atoms coming through would be exactly the same thing. The fraction that get absorbed is equal to the number of photons coming through divided by the number, the number that actually get absorbed divided by the number coming through. Like, in other words, if half the photons were getting absorbed, then the number of photons getting absorbed every second would be half of the number of photons taking a chance at getting absorbed every second. So that's why these absorption cross-sections are effectively areas like that. It's the effective area that each atom is presenting to a beam of photons that determines how many photons it's going to absorb. You don't look entirely happy with what I'm saying.
No.
Okay, you're still saying.
Very acceptable.
Very upset. Okay? So here is how things work out. So notice that it goes like 1 over n to the 5th power. So in other words, as n goes up, as the electron gets further from the nucleus, then what's happening to the absorption cross-section? So this is n, right, is showing up here. So as n increases, what happens to the absorption cross-section? It goes down, and it goes down rapidly with n, is the way it works out, because of the 1 over n to the 5th power. We will note this is comparable to the collision cross-section that we wrote down before. Which was I times 2a squared, where a was the Bohr radius, which for hydrogen worked out to be 3.52 times 10 to the minus 20th power square meters. Well, here we've got 1.3 times 10 to the minus 19 power square meters. And so those are comparable to one another, is what it comes down to. So the atom, a hydrogen atom, quote unquote, looks about as big to photons as it does, photons on the order of 500 nanometers wavelength as it does to whatever I'm trying to say, to other particles. Yeah, fine, collision cross-section. So, that's bound-free absorption or photoionization. Are we ready to move on to the next one? Sure, why not? And there was much rejoicing.
And then there was 2.
There was much rejoicing. There was also a smattering of consternation. But I like Robin.
We already lost it.
Wait, what? Genesis. Oh, really?
Wait, what?
Genesis
Genesis?
dropped down to 8.
Oh, she did?
Yeah.
Ooh.
Yeah.
Oh,
Yeah. It's unfortunate, but
it is unfortunate.
there's a lot. But
Should.
she'll continue on. Lost.
Okay. All right.
But you can't kick me out. Well, how are you smelling that?
There's an album by the group Genesis called "And Then There Were Three," which is kind of like, yeah, because Peter Gabriel left Genesis, and there was, I'm trying to wait. So yeah, so when Peter Gabriel left, there were 3 members left, and so it's "And Then There Were Three."
That's sad.
Yep.
It's like Fleetwood Mac. I know we was fighting all the time, so they made that whole album. But they just like needed to work out their differences. So they just like everyone had a song and they were just like, okay, we're gonna work out our shit and not break up.
Yeah. Yep. Well, Fleetwood Mac went through so many, I mean, early Fleetwood Mac, you can't even, it's completely different from later Fleetwood Mac. Yep.
So many people.
Yep. All righty, anyway, next we have free absorption. This is like hippie absorption. Electrons that start free, they end free. Free absorption occurs when a free electron near an ion absorbs a photon and thus picks up speed. And it has a good German name, which we'll give in a moment.
I don't know if I have enough room to write a German name in my paper.
What's that?
I don't know if I have enough room to write a German name in my paper.
It's only, what is it? It's 57 letters. It's not.
Sounds about right.
Occurs when a free electron near an ion, I can't resist what I'm about to do, near an ion, absorbs a photon, and thus increases its Geschwindigkeit. Do you remember what Geschwindigkeit is? Yes.
Some simple word. Increases.
Damn it, Germany, what?
It's so much more fun in German.
It's like Lord of the Rings when like they meet the tree people and they take like days to say hello.
Oh, really?
Yeah. It's like they just, I don't know. That's what the German language is going for.
It's pretty much, yeah. Yep. It's good stuff. It's like I was saying at E&M, right? It's like, or no, did I say, yeah, I said that to you guys in E&M. Physics is more fun in German.
Oh, yeah.
Right, in English, acceleration is the rate of change of velocity, but in German, Beschleunigung is the rate of change of Geschwindigkeit. So here we picked up some Geschwindigkeit. We've got some more kinetic energy because we've absorbed the energy of the photon. The ion is needed so that both momentum and energy can be conserved. As you may recall, that a free electron cannot absorb a photon because you can't conserve both momentum and energy if you absorb a photon and you're just an unstructured particle, something with no degrees of freedom internally. So that both momentum and energy can be conserved. So the picture that is often drawn for this is based on like if you drew a Feynman diagram for it. So there's the electron and a photon comes in. Here's an ion. Photon comes in because classically you wouldn't absorb a photon. Classically this would be a continuous interaction with the electric field of the incoming photon. Quantum mechanically though, you absorb the photon and the electron changes direction and speed. And you need the ion there because the ion has to participate so that both momentum and energy can be conserved, is what it comes down to. Now, every process like this has an inverse, right? In other words, for free absorption, there's also free emission. The electron jumps down, that's free emission. For bound-free absorption, there's also bound-free emission, where an electron recombines with an atom and gives off energy as a result of that. And there's an inverse process to this as well. You can have an electron slow down in the presence of the ion and emit a photon as a result, and that's what has the cool German name. The inverse process, wherein an electron near an ion slows down and emits a photon, is called, and even English-speaking astronomers call this because the German name stuck, because how could it not? It's too cool. Bremsstrahlung. Or Strahlung means radiation. And the Brems comes from the word for break, as in slow down. So it's called braking radiation. In other words, radiation due to slowing down. Braking radiation auf Deutsch, in German, in other words. Classically, the classical version of this is when an electric charge accelerates, it radiates. Or as we'll want to put it, when an electric charge has Beschleunigung, it exhibits Strahlung. And maybe I'll just throw that in there too, so later.
What the hell was that?
Yes,
So, how does a ion conserve both momentum and energy?
you need them both. In other words, the ion is said, it's not quite true, but the ion takes up the momentum, in other words. So the idea is that if you write down the combined moment, you can, if you say, okay, the initial momentum is the momentum of the photon, and the initial energy is the energy of the photon. Imagine that the electron, you can imagine the electron and the ion were initially at rest, and then they don't have to, but you can imagine that. Photon comes in with some energy and some momentum. If you just try to make, if you just try to say, okay, the photon disappears, and then the electron has its momentum and energy afterwards, it doesn't work. You can't make it happen because the way momentum works in relativity. In other words, a photon's momentum is pc, but the particle's momentum at low velocity would be mv. Its kinetic energy would be 1/2 mv squared. You can also write down that correct relativistic relation, and it just doesn't work. You can't make it. You can't make the before and after momentum equal. But if you say, okay, the combined momentum of the atom, of the ion and the electron, and the combined energy of the ion and the electron afterwards is the energy and momentum of the photon before, you can make that work, is what it comes down to. So the ion will be moving a little bit afterwards. It has most of the momentum afterwards, and the electron has most of the kinetic energy afterwards, and you can make it work, is what it comes down to. So you need two particles, in other words, in order to carry away both the momentum and the energy of the photon.
So it's still absorbed by the electron.
It's really absorbed by the pair. But because the electron takes most of the energy, we tend to sloppily think of it as being absorbed by the electron, but it's wrong. It's actually the pair of them that are absorbing the photon.
Okay.
Yeah. Even scientists are sometimes sloppy. Like, for example, I'll say, I'm giving this eraser potential energy by raising it higher off the ground. It's not really right. The potential energy belongs to the Earth and the eraser. It's the system, Earth plus eraser, that is changing its potential energy. But we get sloppy and we say, oh, it's energy, I'm increasing the energy of the eraser when I'm doing it. But it's really both. It's the Earth eraser system that is changing its energy. And this is a similar situation. It's really the ion-electron pair that is absorbing the energy and momentum of the photon. And it turns out that the ion has very little kinetic energy but most of the momentum, and vice versa. The electron carries very little of the momentum but most of the kinetic energy after the absorption. Next up is electron scattering. And it's pretty easy to figure out what this refers to. It would refer to scattering of photons by electrons. I know that's profound. Electron scattering occurs when photons are scattered by free electrons rather than absorbed. An electron can't absorb a photon by itself, but it can redirect a photon. You can have it where a photon comes in and it changes direction and gives some momentum and energy to the photon, and the electron's momentum plus the photon's momentum afterwards equals the photon's momentum before, same deal for the energy. That you can do. You just can't completely absorb the photon. You can't make it go away. Electron scattering occurs when photons are scattered by free electrons. Scattered again means their direction is changed. This is also called Thomson scattering. I think I've spelled that correctly. There's a lot of people that are Thompson with a P in there. So I don't know, there's no P in my notes, but I don't remember if that's because this person's name really had no P or if I just left the P on. Which means I never will because I forget. But yeah, but go for it. That's right. That's why we have smartphones.
Those are supercomputers in our pockets.
Yes. That we use to post pictures of cats.
Exactly. I
Yes.
believe you were right.
So I have all of human knowledge in my hand and use it to post pictures of cats. Yes.
There's no P.
There is no P? All right, I feel good then. So, the Thomson scattering cross-section, sigma t, works out to be, so if we start with the Schrodinger equation, works out to be 8 pi over 3 times E squared over the mass of the electron c squared. squared. So charge on the electron over MC squared for the electron squared equals 6.65 times 10 to the minus 29th power square meters. Notice that's way smaller than the numbers we were getting before for like the collision cross-section and so forth. Independent of lambda, but that's an eccentric behavior, but that's because before we were talking about atoms. For this guy, this is for an electron, which is much smaller than an atom. So the thing to notice is it's independent of lambda. So since the Thomson cross-section is way, way smaller than the bound-free absorption cross-section, Thomson scattering becomes dominant only in very hot stars where everything is ionized. In the atmosphere, I should say, because it dominates in any star deep in the interior where everything is ionized. In the sun's core, everything is ionized. It's way too hot for electrons to be bound to nuclei. So electron scattering dominates in stellar interiors and in the surfaces of very hot stars. Becomes dominant only at temperatures high enough that everything is ionized. Because otherwise you'll get a much bigger contribution from ionizing atoms than you will from scattering off of free electrons. Temperatures high enough that everything is fully ionized. So that would be stellar interiors and the atmospheres of very hot stars. So Brad Pitt, Thomson scattering dominates, for example.
Young Brad.
Young Brad Pitt. Oh, no.
No.
He's timelessly hot.
Tom Hanks is timelessly hot.
There you go.
You wanna go on Man Crush, dude?
Huh?
You guys go on your celebrity Man Crush faces?
Bro, Tom Hanks is like the greatest.
No.
Oh, fight
That's so cool.
Just go to throw hands.
I'm going to extract that part of this video and post it on Facebook. Look what I started in my class today.
I love you, Tom Hanks. Just keep on keeping on. Don't listen to these haters.
All right, so we will add here. Photons can also scatter from loosely bound outer electrons in atoms, and that's called Compton scattering if the wavelength is much smaller than the atom, and Rayleigh scattering if lambda is much bigger than the size of the atom. Photons can also scatter from loosely bound outer electrons in atoms. Which is called Compton scattering. the wavelength of the photon is much, much less than the size of the atom. In that case, the photon just kind of sees the electron by itself, if you will. And truth be told, often scattering off the free electrons is called Compton scattering by physicists. So Compton scattering, if the wavelength is much less than the size of the atom, and Rayleigh scattering, if the wavelength is much bigger than the size of the atom. And Rayleigh scattering, that cross-section goes like 1 over the wavelength to the 4th power. So what's a typical wavelength for visible light? Yeah, 400 to 700, so in other words, visible light's on the order of 500 nanometers, a few hundred nanometers. What's the size of an atom or a molecule, roughly speaking? How big is a hydrogen atom, roughly? Not that small. This is one of these things you just want to know. No. About an angstrom, about 1/10 of a nanometer, right? 10 to the minus 10 meters is a typical atomic size. So in other words, about 0.1 nanometer for atoms. And molecules are bigger because they're chains, right? So, are we in, for visible light, are we in the Compton regime or the Rayleigh regime? Is the wavelength much smaller than the size of the atom or much bigger than the size of the atom when light scatters off of air molecules, for example? Wavelength of the light, a few hundred nanometers. The size of the air molecules, a couple tenths of a nanometer. So which regime are we in? No, I'm saying it's Compton scattering if the wavelength is very small compared to the size of the atom. Rayleigh scattering if the wavelength is very big compared to the size of the atom. Wavelength, hundreds of nanometers, atom size, fraction of a nanometer. So we are in the Rayleigh regime. Yeah, we're in the Rayleigh regime. So visible light scattering is in the Rayleigh regime. So the scattering goes like 1 over lambda to the 4th power. So, if we look at the scattering cross-section for 400 nanometers, the purple end, versus the scattered cross-section for 700 nanometers, the red end of the visible spectrum, right? right? Then that's gonna be 7/4 to the 4th power, right, because it's the reciprocal of the wavelength. What's 7/4 to the 4th power? Quick, you've got phones. This would be easy if it was like 350 millimeters. Or calculators. You've got calculators or phones or
9.379.
9.379. So okay, so like 37, so about 9.4. So purple light is scattered 9 times more than red light is. Blue light scattered not quite 9 times, but still a lot more than red light is. So air molecules scatter blue a lot more than they scatter red. What phenomenon is this responsible for? Blue sky. This is why the sky is blue. This is why the sky is blue. This is why the sky is blue. Air molecules scatter short lambdas much more than long lambdas. That's why the sky is blue. So if your parents ever told you the sky is blue because it's reflecting the ocean, you should say, no, actually the sky is blue because of the inverse 4th power dependence of the cross-section for Rayleigh scattering. And then they'll say, you know what? My tuition is paying off that I'm paying.
Boom,
Yes, that's right, yes. All right, time to take a break. There's an XKCD where I think it's like there's this little girl who's like saying to her mom something like, then why isn't the sky purple? And mom was like, you know, blah, 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 blah. She's like making up some BS. But the reason the sky isn't purple is that our eyes have receptors that are more sensitive to, we have red, green, and blue receptors basically. So our eyes are a bit more sensitive to blue than they are to violet. And the sun makes more blue than violet. So put it together and we perceive it as blue. But strictly speaking, yeah, purple is scattered. As a fraction, purple photons are scattered more than blue photons too.
Could we ever have a green sky?